Alright, so today we're going to give a quick classic proof that every polynomial of degree greater than or equal to 1 has at least one complex root. So this is known as the fundamental theorem of algebra. It can also be stated as saying that the field of complex numbers is algebraically closed. Okay, so we start our proof with the Cauchy's formula. So we're going to assume that you know some complex analysis, just enough to define the Cauchy formula, the version for derivatives. So we have a complex analytic function f. We know that its kth derivative at a point a in the complex plane divided by k factorial is equal to 1 over 2 pi I times the integral over gamma r. I'll say what gamma r is in a second, of f of omega divided by omega minus a to the n plus 1 d omega. Okay. Or sorry, I should probably put a k here. Okay. K plus 1. Now, this gamma r here is simply the curve that follows a circumference in the complex plane. So this is equal to a plus e to the I theta. So this is just the curve that goes around the circle of radius. So I should probably put r here. R e I theta. So this follows the circumference of the circle of radius r centered at a in the complex plane. And the domain of gamma r is just the interval from 0 to 2 pi. Okay, so this is gamma r. And we have this formula here, which is Cauchy's integral formula. And we're going to use Cauchy's integral formula to get a bound, the Cauchy estimates on the derivatives of f. And so to do that, we're just going to apply the supremum bound on the integral. So first, what we're going to do is send this k to the other side. So let's erase this k from here, k factorial. And now we're going to just take the absolute value of both sides. So absolute value of the derivative of f is going to be less than or equal to the absolute value of the other side. And we can bound the other side using the supremum inequality on the integral. So that's going to give us k factorial 2 pi I times, we can, first of all, let's take actually, first of all, we should assume, yes, let's just assume, actually, first of all, as a hypothesis to get this bound here, we assume that this f is actually bounded by a real number n less than infinity. Okay, so this is the hypothesis. So f is actually a bounded analytic function, and now we can go ahead and say so f is bounded, so we can use that to say that we have just the integral of the absolute value of the integrand here, which is going to be less than or equal to, let's copy and paste this guy, you can pull that that f of omega out to get this. Okay, so now we still have to bound this integral, and now we'll use the supremum inequality. So we can go ahead and notice that this omega minus a here is equal to r, which is the radius of our circle. So we have a here, and omega we're integrating over this circle. So the distance between a and omega is always going to be the radius of the circle r, or I guess little r. We denote it by little r. So this in absolute value, this is just equal to 1 over r to the k plus 1. Okay, so we can pull that. We can bound the integral actually by so 1 over r to the k plus 1 times, so this is the supremum of the integrand, times the length of the curve we're integrating over, so that's gamma r, and the length of this is just the circumference of the circle of radius r, which is equal to 2 pi r. So we multiply this by 2 pi r. Okay, and so now this 2 pi is going to cancel out with this 2 pi. We can also notice that the absolute value of 1 over I is just 1, so we can remove this I from here. And what else do we have? We have, okay, so we have an r here, and that's going to cancel out with this plus 1. So in the end, we have this bound. We have k factorial m over r to the k. And this is the Cauchy estimates on the derivatives of f. Right, so what we end up with is the kth derivative of f at the point A is bounded by this. This is the Cauchy estimate. Okay, so now we can use this Cauchy estimate to prove a theorem called Liouville's theorem. And Liouville's theorem states that if we have an entire function, so an entire function is just an analytic function on the whole plane, so entire function, and if it's bounded, so if we have a bounded entire function actually, bounded entire function, this implies that the function, let's say bounded function f, then this implies that f is constant. Okay, and the proof of this is just a simple application of this Cauchy estimate because, well, all we need to do is show that the derivative of f is 0 everywhere. And in fact, so the derivative of f is just taking k equals to 1 in that estimate, so I have 1 here. At an arbitrary point, a is less than or equal to m over r, and so we assume that f is bounded, and so m is r bound on f, and since the function is entire, we can take r tending to infinity, and the same estimate holds for every r that we take. So in fact, this entire side over here tends to 0, and so does the left hand side, and since a was arbitrary, we have that the derivative of f is 0 everywhere, and so f is constant. Okay, so that's Liouville's theorem, and using Liouville's theorem we can prove our original proposition, which is that every polynomial of degree d greater than or equal to 1 has at least one complex root. And so let's prove that here. So now the proof of the fundamental theorem of algebra, we're going to do this by contradiction. So suppose for contradiction that p of z, which is our polynomial that we fixed, so polynomial of complex coefficients, integer exponents, suppose it doesn't have a root in the complex plane, doesn't have a single root in the complex plane, so p of z is not equal to 0 for every z complex. Well, so we know that this is an analytic function, right? It's a polynomial. It's better than analytic. And so that means, since it doesn't have a root, we can invert it and get another analytic function. So define the analytic function g of z by 1 over p of z. This is an analytic function. It's well defined because p of z doesn't have a root. Now we just apply Liouville's theorem. On g of z. And to apply Liouville's theorem, we just need to show that g of z is bounded, and in fact it's bounded because we can use, that old trick of, if we have, let's say that this is the domain, this is the complex plane. Well, I guess we can draw it in 2 dimensions. If you have the complex plane here, and so this is the domain of g of z, then we have that in a certain region, we can take, since it's continuous, and we can take this, I don't know, maybe a closed ball here. It is so it's compact here, and it's continuous, so it's going to have an upper bound in this region. So let's say the upper bound is m, right? We can maybe say m prime, considering the upper bound of, wait, well, yeah, we can say it's m. So this is the upper bound m, and then outside of this region, it's also going to be bounded because of the fact that because of the fact that g of z tends to 0, or the absolute value of g of z tends to 0, as the absolute value of z tends to infinity. And this happens because the absolute value of p of z tends to infinity as z tends to infinity, because p is a polynomial. And so since g of z is the inverse of it, we can say that, I guess I can be a little more formal here. We can say that there exists, because of this bottom part here, we can say that there exists in order, let's say big R, I don't think I use big R, it's a big R greater than 0, such that if a complex number is an absolute value greater than R, then p of z is going to be greater than or equal to, let's say maybe p, big P. Okay, and so we just invert this basically for g. So we say that that for this R, if z is greater than or equal to R, then g of z is going to be less than or equal to 1 over p, basically. So outside here, we have that the bound on g is 1 over p. Okay, and so we just take the greatest of m and 1 over p, and that is the bound on g of z. Okay, so g of z is bounded. So bound of g of z is the maximum of m and 1 over p, whichever is greater. And okay, so now we can apply Liouville's theorem, right? Because g of z is an analytic bounded function, so that means it must be constant. But so that implies it's constant. But that means that 1 over p. That means that 1 over p is constant, which implies that p is constant, which is a contradiction because we assumed that p is of degree greater than or equal to 1. Okay, so, and that proves the fundamental theorem of algebra.